We've defined our trig functions in terms of a point on a unit circle. A unit circle has radius 1, and for a point on the edge of the unit circle, pretend this is the unit circle with radius I tried to write in green here of 1, cosine theta is going to be the x-coordinate of that point. Here I've called it x1. Sine of theta is going to be the y-coordinate, which here I've called y1, are the coordinates of point P1 here. So a circle of radius r, which I've drawn here, which could be larger than 1 or smaller than 1. The point is it's not 1. You're going to have a point on a different circle. And so this ray is going to extend, this has length 1 to go to point P1, the length r goes all the way from the origin to point P2. So x2 here is our length all the way over to here, y2 is the point all the way up to here. So what we have here is we have a case of similar triangles, where these triangles, the smaller one that I tried to draw in green and the bigger one in purple, have the same interior angles, which means that the bigger one is just a blown up version of the smaller one. So we have these proportional relationships here. R over 1 should be the same ratio as x2 over x1. So if the purple triangle is twice as big, this would be 2 over 1, and this would be, this horizontal distance here would be twice as big as this one. And same thing here, although I don't know why I wrote R2, I just meant R. This radius over 1 should be the same as the ratio of the y distances. So we remember here that we know that cosine of theta is going to give us x1, where theta is this counterclockwise rotation in here. So we could just put that into our formula, and r over 1 is just r, so we can say r equals x2 over cosine theta. And then we'll multiply and divide on both sides. We get cosine theta equals x2 over r. Similarly here, we know that the sine of theta equals y1, so we just put sine of theta in for y1. R over 1 is just r, so we get r equals y2 over sine of theta, or just multiplying both sides and then dividing again, we get sine of theta equals y2 over sine of theta. So now we can summarize. On a circle of radius r, cosine theta equals x divided by the radius. This is the x-coordinate of a point P on the circle, and y is the same thing. So cosine theta is x over r, sine of theta is y over r. So notice we're using x and y for both of these, but they mean different things. Here, x and y is a point on the unit circle. Here it's a point on a circle of radius r. But it kind of works out either way, because if your radius was 1, you notice you'd have x over 1, which would just be x. Y over 1 would just be y. So if you're going to memorize just one formula, memorize these, because these are going to work in every single situation. If you're on a unit circle, just put 1 in for r. These are your more general, high-level formulas you can use anytime. But there's one more thing we can do here, just with a little bit of multiplication. Up here we said x was the x-coordinate of a point P on the edge of the circle of radius r, so just turn this around, multiply both sides of this by r to solve for x alone. So if a problem in this class or some application, you had a point on the edge of a circle of radius r and you need to find its coordinates, it would be r cosine theta, r sine of theta. So any circle you might draw like this, suppose the radius is 6, and you want to find this here. Suppose theta is, I don't know, 72.3 degrees, and you have a point P here. Then the coordinates of this point, P is going to be equal to 6 times cosine 72.3 degrees, comma 6, comma sine 72.3 degrees. And I know I didn't plan my spacing very well here, but it's an important formula that you're going to get a lot of use out of.